In this video, we're going to go over ways to communicate equilibrium position. So what that means is ways to communicate whether products are favored or reactants are favored, or if the reaction is quantitative. The other thing that we're going to be doing in this video is we're going to go over how to interpret equilibrium graphs. So there's a few different ways in which we can communicate equilibrium position. So the first way is through words, so that's by saying whether products or reactants are favored. We can communicate it through arrows, and typically what we do is we would include a percent of reaction over top of the equilibrium arrows to show whether products or reactants are favored. And then for the third way, it will be equilibrium expressions and the equilibrium constant. So the equilibrium constant, what value it is, tells you whether products or reactants are favored. And then the last way is through graphs. Okay, so if we're trying to say that the forward reaction is favored or the products are favored, one way to communicate that is just by saying products are favored or the forward reaction is favored. Okay, either or works. Okay, so what this means is that you have a higher concentration of products compared to reactants. So remember that the square brackets mean concentration of, and it's concentration of whatever is inside of those square brackets. Actually, I'll write that up there. Square brackets mean concentration of. Okay, so here this is saying the concentration of the products is bigger than the reactants when the forward reaction is favored or when products are favored, okay, in an equilibrium. So how we would represent that with arrows is we'd go like this, but to represent that the forward reaction is favored, if we're only using arrows, we would add another arrow going like this. But typically the more common way to see this communicated is by seeing this. So we'll say greater than 50%. So what this means here is that more than 50% of the products are being formed. So that indicates to you that the forward reaction is favored with this, or in other words, the products are being favored. All right, so if we want to say that the reverse reaction is being favored, we can either say reverse reaction is favored or reactants are favored. So what this is meaning is that you're going to have a higher concentration or a bigger concentration of your reactants compared to your products. So how we would communicate this with arrows is we'd write our equilibrium arrows and then we'd write a backwards arrow to show that the reverse reaction is favored. But again, the more common way to see this communicated would be to say that less than 50% of your products are being formed, which tells you that the reactants are favored if less than 50% of your products are being formed. Okay, and if the reaction goes to completion, how we would communicate that is we'd say that the reaction is quantitative. So that means that you're essentially producing 100% or more than 99% of your products, and you have almost no reactants left over. So how we would communicate that with arrows is you just have your forward reaction arrow, and with equilibrium arrows, you would communicate it like this. So greater than 90% of your products are being formed. So an equilibrium can be quantitative to the reactant side if no appreciable product is produced. So what that means is if your reaction basically produces no products, then the reaction or equilibrium can be qualified as quantitative to the reactant side, which means we would represent that with a backwards reaction arrow. So just as a reminder that in a chemical equilibrium, there's a constant ratio between the concentration of the products and the concentration of the reactants. So that is what your equilibrium constant, which is K, represents, is that ratio of your concentration of products compared to the concentration of your reactants. So you do need to understand what K, or your equilibrium constant, represents. And keep in mind this comparison between your concentration of your products and your concentration of reactants. All of these concentrations are taken from the equilibrium concentrations. Okay, so eventually when we get into ICE tables, we'll be looking at initial concentrations, how those concentrations are changing, and then the equilibrium concentrations. That's why I'm trying to just remind you guys, or say it frequently, that your equilibrium constant takes the concentrations from your reactants and products at equilibrium. All right, so a larger equilibrium constant means that you have more products present at equilibrium. And a smaller equilibrium constant means that you have a higher concentration of reactants at equilibrium. Okay, so if you wanted to include some more mathy terms to represent this, is the concentration of your products are going to be proportional to your equilibrium constant. Whereas the concentration of your reactants are going to be inversely proportional to your equilibrium constant. So what that means, if I write out a quick equilibrium law expression, so I have concentration of products divided by concentration of reactants. So proportional, what that means is if your concentration of your products goes up, your equilibrium constant will increase in value. If the concentration of your products goes down, then your equilibrium constant will decrease in value. Okay, so what happens to one happens the exact same to the other. Okay, when one goes up, the other goes up for two things that are proportional to each other. And likewise, when one of them goes down, the other one does as well. So that's just what I mean by a proportional relationship. Okay. Meanwhile, for reactants, if the concentration of reactants increases, because there's an inversely proportional relationship between your equilibrium constant and your concentration of reactants, when one goes up, the other one goes down. That's what inversely proportional means. When one thing happens to one of them, the opposite happens to the other. Okay? So then when your concentration of your reactants decreases, then your equilibrium constant increases. All right, so let's talk about some values so you can figure out when products are favored versus when reactants are favored just by looking at your equilibrium constant here. And you know what? I'm going to make an additional note here just above, just to capture what we're talking about here. So the value of your equilibrium constant tells you whether reactants or products are favored. Okay, so what values are you looking for to tell you whether products are favored or reactants are favored? So if your equilibrium constant is a lot bigger than 1, then your products are favored. Okay, another way you could communicate that the forward reaction is favored or your products are favored is you could say that your equilibrium lies to the right or is shifted to the right. So K or Kc, both of them mean the equilibrium constant. So what this means here is if your equilibrium constant is a lot bigger than 1, products are favored. Meanwhile, if your equilibrium constant is a lot smaller than 1, then your reactants are going to be favored. So what this is saying, I'm just writing it out. If your equilibrium constant is a lot smaller than 1, reactants are favored. Now, a reason that we can say that your equilibrium lies to the left when your reactants are favored, it's just because your reactants, when you write out chemical reactions, your reactants are on the left-hand side of the reaction arrow. So that's what this means. Similarly, when we're trying to say that your equilibrium lies to the right to represent that products are being favored, it's just because your products are on the right-hand side of your reaction arrow. All right. And if your equilibrium constant is around 1, then the concentration of your products and reactants are going to be the same. Okay, so just as a heads up there, your equilibrium constant will never be a negative number. So when we say your equilibrium constant is a lot smaller than 1, we're not meaning that the equilibrium constant turns into a negative, right? You're just talking about a very small number, somewhere in between 0 and 1. Okay, so for some examples here, if you're trying to represent that your reactants are favored, right, what that might look like for an equilibrium constant is maybe the value is going to be, actually, let's go 2.5 times 10 to the negative 6. Okay, so what this is, if we weren't writing this in scientific notation, is it would be this number. Right, so this is a very small number, so it's a lot smaller than 1, and so this would represent that your reactants are favored over your products for this equilibrium that we're talking about in this example. So talking about equilibrium constant numbers, we do need to refamiliarize ourselves with scientific notation and just understanding what numbers are bigger in scientific notation versus what numbers are smaller. So typically your small numbers are going to have a negative exponent. So all of these numbers here after the times by 10, they should be superscript to represent that they are exponents here, but there's that small typo in the notes here. Okay, so just so that you're aware. All right, so let's put these numbers in numeric order, and we're gonna put them from smallest to largest. So how we're going to determine this is, first I'm gonna look for the smallest exponent. So what that means is the most negative exponent here. So that's going to be this 2.8 times 10 to the power of negative 6. That negative 6 is our smallest number. So that number is our smallest one. So I'm going to, just for the sake of space, because I don't have a lot of space here, I'm going to write the 6 to say that it's this number, that's number 6. Okay, so moving on here, okay, we're going to look for the next smallest number. Okay, so that's our times by 10 to the negative 5 values. So because they're to the same exponent, then we got to move on to comparing like the numbers in front of the times by 10. So we're comparing 2.2 versus 3.5. So obviously 2.2 is the smaller of the two numbers. Okay, so we'll put this number next because it is bigger than a number to the power of negative 6, but it's not as big or bigger than the 3.5 times 10 to the negative 5. So I'll say 1, 3, so that takes care of these two numbers here. Then we're moving on to these numbers. So again, we're comparing 1.4 to 1.5 because both of them are raised to the same exponent here. So 1.4 is smaller. So I'll go number 2, then number 4. So that takes care of those two. And then last but not least, we have our 2.2 times 10 to the power of positive 3. So that's number 5. So this has a positive exponent, so it is going to be a bigger number than all of our numbers that had the negative exponents. Okay. So just as a reminder here, any number with a negative exponent you're moving the decimal to the left to go from scientific notation to the normal way to write the number. So for example, let's say I was writing this out as a normal number, right? The exponent is telling me that I'm moving my decimal from here 4 spots to the left. So what that would look like is this, right? So we moved our decimal 1, 2, 3, 4 spots over to the left in order to get this number here. Both of these numbers are the same, just one is in scientific notation, the other one is just written as per normal. Okay? But if we're talking about a positive exponent, this tells you that you're moving your decimal to the right, and since it's a 3, it would be 3 spots to the right. So positive exponent means you're moving your decimal to the right, and then the value of that exponent tells you how many spots over to move it. Okay, so this would be that. So I've moved my decimal 1, 2, 3 spots over to the right here to go from scientific notation to the normal way to write numbers. Okay, so as you can see, numbers with a positive exponent, they are bigger than 1, whereas numbers with a negative exponent are between 0 and 1 there. All right, so let's do the same for this set of numbers over here. So again, all of these values behind the times by 10, they should be superscript. So just a heads up on that, all of these are exponents. So we've got to place these equilibrium constant values in order from most favoring products to least favoring products. So as we said before, the bigger the equilibrium constant, the more that your products are going to be favored. Okay, so since we're starting with most favoring products, that means we're starting with our biggest number. And we're going to our lowest equilibrium constant, which would favor or be least favoring the products. That's what I should say. All right, so since we're looking for our biggest equilibrium constant, that means I'm going to start off by looking for my biggest exponent, and that looks to be like this number, 1.7 times 10 to the power of positive 2. So I'll say, just to save on space, so our equilibrium constant for value number 4 goes first. That's our biggest equilibrium constant. Now we're looking for our next smaller one. So that looks to be like this one here. Okay, so the reason why I'm choosing this is because -3 is still bigger than either -5, -7, or -8. Okay, now the next smallest number is going to be -5, or the next smallest exponent is going to be -5, then -7, and then for our last two numbers, they're both to the power of -8. However, we got to compare the values in front of the times by 10. So 2.2 versus 2.1, the bigger of the two numbers is the 2.2, so value 1 goes first, so that would be this one, and then value number 2 would be just a tiny bit smaller there. Okay, and that's just because 2.2 is bigger than 2.1. And again, we're focusing on the numbers in front of the times by 10 to the power of 8, negative 8, just because when you have the same exponent, you got to focus more on the number in front. All right, so there are some limitations of equilibrium law expressions as well as equilibrium constants. So they don't provide the information on the rates of reactions. They only tell you the relative amount of products and reactants at equilibrium. Okay, so they're only telling you like if your products have a higher concentration compared to your reactants, or if your reactants have a higher concentration compared to the concentration of your products. One thing that you should know about equilibrium constants is they are only going to be affected by temperature. Okay, so depending on what type of reaction it is, whether it's an endothermic or exothermic reaction, is going to determine whether if you do something like raising the temperature, if your products or your reactants are going to be favored there. Right, so if you have an endothermic reaction, which requires energy or heat in order to get the forward reaction to go, if you increase temperature there, then your products will be more favored, or your equilibrium will shift to the right. Right, but if you have an exothermic reaction, so you could think of exothermic as heat is exiting the system, so you would expect heat to be a product of that particular reaction. If you increase the temperature on an exothermic reaction, then your equilibrium will shift to the left and your reactants will be more favored. Okay, which in terms of your equilibrium constant, if your reactants are more favored, then your equilibrium constant will decrease compared to the value it was before you increase that temperature. Okay, now percent reaction, so percent reaction, those are the values that we are putting over top of the reaction arrows. Percent reaction has a different value for every change in initial concentration of reactants, and typically you only use percent reactions for 0.1 mole per liter solutions. This, I would say, knowing this statement is a lot more important than this statement here, okay, because the equilibrium constant being affected by temperature is a lot more useful piece of information. All right, so equilibrium graphs. On your x-axis, that's always going to be time, or you could call it the reaction coordinate. On your y-axis, you're going to have your concentration of reactants and products, which are usually going to be in moles per liter. The concentration of your reactants typically decreases, especially as the forward reaction happens, and the concentration of your products are increasing as the rate of increase and decrease are proportional to the coefficients of the equilibrium. So that's basically what this is saying is if you see a line that's increasing in concentration, that's going to tell you that that's going to be your product. Whereas if you see a line that's decreasing, that tells you that that belongs to a reactant. Okay. And then last but not least, equilibrium is reached if all lines are parallel. So the important part about that is that oftentimes students think that where the lines cross is equilibrium, or is when equilibrium is reached. However, that is not true. So that's very important to understand where the lines cross. That is not where equilibrium is reached. Where equilibrium is reached is when the lines become parallel. So all it means, all this point means, is just that the concentration of your products is the same as the concentration of your reactants. Okay, so where the lines cross isn't where equilibrium is reached. It's just the point where the concentration of your products is equal to the concentration of your reactants. Okay, where equilibrium is going to be reached is when the lines become parallel here. Okay, so for the first question, what time was equilibrium established? Really what that question is asking is, when do the lines first become parallel? All right, so there is a little bit of leeway here. I would say they first become parallel right at 70 seconds here. Okay, but if you're thinking that maybe they became parallel just a slight bit earlier, you could say something like 68 seconds. Okay, but I'm gonna say 70 seconds. All right, second question is, what is favored, either the products or reactants? And really what this question is asking is, which one do you make more of? And if you want to think of it more visually, it's asking which line is higher on the graph once equilibrium is reached. Okay, so once the lines become parallel. So the reason why the higher line on the graph tells you what is favored, either your reactants or products, is because the higher line corresponds to more concentration. Okay, so if you have more concentration of something, you're going to have more of it. So whatever you have more of is going to be favored. So in this case, because the blue line is higher, and that belongs to one of our products in this situation, we could say that the products are favored. And last but not least, what is the value of the equilibrium constant? Well, let's set up a quick equilibrium law expression here. So in the absence of an actual reaction for this equilibrium graph, I'm just going to use concentration of products divided by concentration of reactants. Okay, if the question doesn't say whether it's the forward or reverse reaction they're asking about, you always assume the forward reaction, so that's why products are divided by reactants. Okay, so let's read this graph here. Okay, so products, that is at about 3.5 mole per liter. And usually you would raise it to the power of whatever coefficient is on your product. However, because we don't have a balanced chemical reaction to pull our coefficients from for our exponents, I'm just going to leave it at 3.5. divided by, so our reactants is at a concentration of 2. So, by the way, this is 2 moles per liter and 3.5 moles per liter here. Okay, so 3.5 divided by 2, that's going to give us, let's just divide it real quick, 1.75. And remember that equilibrium constant, the value you get for that is going to not have any units there. Okay. What I'm going to do here, this isn't perfect, so because we're using a graph, the values aren't really perfect, but for the sake of sigdigs, I'm going to put this as 2.0 instead of just 2, just so that I can use 2 sigdigs instead of just 1. But again, this isn't a perfect way to decide significant digits. I'm just doing this for the sake of this question. Questions on the test will be a lot more clear as to how many sigdigs you should be putting. So then that'd be an equilibrium constant of 1.8, and remember, no units are required for your equilibrium constant. So just down below here, we have some more examples of equilibrium graphs here. So for the forward reaction going from substance A to substance B, right? Substance B is our product, so you can see that as the forward reaction happens, the concentration of substance B increases. Whereas, again, as the forward reaction happens, our reactant decreases in concentration, which makes sense because as the forward reaction happens, products are being produced and reactants are being used up. Now, for the reverse reaction here, because we're going from our products to our reactants, the reactants are being produced, right? So that's why the concentration of the reactants or substance A increases. Whereas for the concentration of substance B, it decreases because we're using up substance B in order to produce substance A. Okay, so on this next page here, there is a little bit of blurb of information here. So nothing in here or on this last part of this page here is something that you have to memorize. So these equilibriums you don't have to memorize here. This is just a little bit of information just for fun. However, you should be aware of what the Haber process is or the Haber-Bosch process. You could use either name. So the main part from this last part of this page is that you should know the Haber process, which is also known as the Haber-Bosch process, which is a way to produce ammonia from atmospheric nitrogen and hydrogen gas. So the reason why it's called the Haber process or the Haber-Bosch process is just to reference the scientists that first studied this particular reaction. So sometimes questions will say in the Haber process or in the Haber-Bosch process, and that is their way of telling you what reaction you're dealing with. So that's why I'm saying you should know what are the reactants and products for this particular reaction.